Now, let us see how fluid pressure will vary in an accelerating fluid. So, pressure variation in a horizontally accelerating fluid. Now, you see we are studying fluid statics and then we started talking about accelerating fluid. When we talk about fluid static, that means my fluid particles are not in relative motion. The bulk fluid may be in motion, but there is no relative motion between the fluid particles. So, still I can assume that the fluid is static. Let us take an example. So, this is a vessel, wide vessel, which is under an acceleration, horizontal acceleration along A. So, this axis is x axis and this is your y axis. So, now this fluid is like this. So, the level will be somewhat changed, we will see how it is changed. Presently, let us see a cylindrical element, which this cylindrical element's axis is along horizontal. So, consider a fluid, a liquid in a vessel which is horizontally accelerated with A. Let the fluid density be denoted by rho. Now, we consider a cylindrical fluid element whose axis is along x axis. So, you see here, so this length is also dx, this is at a coordinate x. Suppose the pressure is here, so the pressure force due to this P is here, and here the pressure is P plus dP. So, this is the pressure force. So, pressure force is here. So, this vector is a force, and suppose we are the observer in the frame of this differential element. So, we feel a pseudo force, that is dm into A. So, now consider the mechanical equilibrium of the fluid element in the frame of the element itself. So, now you see here the forces in this direction is PdA that is equal to dm into the acceleration plus P plus dP into dA. So, we have PdA is equal to dm mass is dx into d area, that is into A, plus PdA plus dP into dA. So, we have PdA, dA cancelled. Now, again dA will cancel. So, we have dP by dx is equal to minus rho A. Thus, we see that as we move along x, the pressure decreases. So, the rate of pressure dP by dx is equal to minus rho A. So, if I take both this into account, how x pressure varies with x and y. So, we have to write this dou P by dou x along A, along this as rho A, and dP by dy is equal to minus rho g. Now, let us come to this shape. This is called free surface. Free surface. So, let us see that why we have this shape of the free surface, that is how to determine the shape of the free surface. Now, let us see the free surface of the accelerating fluid, that is free surface of an accelerating fluid. So, the fluid is accelerating horizontally. Let us see the free surface, equation of the free surface. So, we have this free surface and I wish to know what is the angle this free surface makes with the horizontal. This is what I wish to calculate. So, what I do? I take 2 points 1 and 2. So, you see here at 1 and 2 and this distance is y1 and this distance is y2, this is here x1 and here this is x2. So, now what I do? Let us find pressure at 1 and 2. So, from the variation of pressure with height. So, we know that the pressure varies with height and we have to know P1 is equal to P atmospheric plus H rho g, that is presently Y1 rho g, and P2 will have P atmospheric plus Y2 rho g. So, the P1 minus P2 is equal to Y1 minus Y2 rho g. So, this we got from seeing the how pressure varies with. So, this pressure is Y1 rho g and this is Y2 rho g. Next, from the variation of pressure with acceleration. So, since we have the fluid accelerating, so we have dP by dx is equal to minus rho a. So, dP is equal to minus rho a dx. So, if I integrate, the pressure is P1 and P2 at 1 and 2. So, x1 and x2, I will get P2 minus P1 is equal to minus rho a x2 minus x1. So, we have P1 minus P2 minus rho a as x2 minus x1. So, this minus has been brought here. So, this is 2. Now, both P1 and P2 is same. So, P1 minus P2 let us equate from 1 and 2 we get. So, this is y1 minus y2 rho g is equal to rho a x2 minus x1. Now, y1 minus y2 you see this is delta y, this rho cancel into g is equal to a into this is delta x, implies delta y by delta x is equal to a by g is equal to tan theta. So, what we got? The relation we got, this tan theta is equal to a by g. So, if a fluid is accelerating, the free surface will have equation, the angle it makes with the horizontal is tan theta is equal to a by g. Now, we can derive this result more easily by looking at the free surface. Let us do now that. Now, let us see that if this is an accelerating fluid with acceleration in this direction, this is the free surface. I wish to know what is this angle theta. So, this is a free surface. What I do? I take a small fluid particle called P here. and draw its free body diagram. So, on this fluid particle there is a mg its weight and there is a pseudo force ma in this direction. So, this is theta, this angle is 90 minus theta and this angle is theta. So, you see here, consider the equilibrium of a fluid particle at the free surface. So, the net force acting on the fluid particle along the tangent or along the surface, that is the free surface, is 0, should be 0, otherwise the fluid will be moving here and there. That is ma cos theta must be equal to mg cos of 90 minus theta. So, cancel, a cos theta is g sin theta, implies tan theta is equal to a by g.